All right, guys. Hope you're doing well. Just want to introduce myself. My name is Shrutik. I'm a rising sophomore at UC Santa Barbara, and I recently switched my major to data science. This is my very first, kind of CS data science project ever, and I'm really excited to share it with you guys. Yeah, hopefully you guys are doing well. I'm gonna go ahead and share my screen now. Um, and yeah, let's just get right to it. So first things first, I want to go over what exactly my project is. So this project is pretty much an audio classifier. It's essentially you have two data sets of audio, one consisting from a dog and a bird, and the program classifies it, right? So as a brief overview of the agenda of what we're going to go over today, I'm just going to go over a brief overview of the project, and then I'm going to go over both the approaches that I use to go ahead and tackle this problem. I'm going to compare the two approaches for you guys, and then I'm going to go over a couple of challenges and potential improvements. So firstly, the overview, as I mentioned earlier, it's an audio classifier that distinguishes between the sounds of a dog and a bird. And there's two approaches to this. The first being a convolutional neural network, which is the more, kind of common approach. And then there's the vision transformer approach, which is the more powerful approach. So pretty much the main idea between both these programs is it creates a spectrogram of the audio. The model trains these spectrograms on what these sounds essentially quote unquote look like. And then the model predicts whether this audio is from a dog or a bird based on the spectrogram visualizations. So if you're unfamiliar with what a spectrogram is, I kind of just scraped some code out of an older version so I can kind of show you guys what it looks like. So this directory variables will be something you'll see commonplace between the demonstrations just for convenience. But pretty much using the Labrosa library, we're able to get MEL spectrogram data, which is essentially just a visualization of the decibels of an audio file over time. And then we can just use PyPlot to, visualize it, right? So this is a sample dog audio. And as you can see, it looks distinct from a sample bird audio. And then this looks distinct from sample noise, which I compiled into a third directory for you guys. So as you can see, they look pretty distinct. And, from a human perspective, you can be like, after seeing enough, you can be like, yeah, that's from a dog, that's from a bird, that's from something else, right? And our goal is essentially to create a program that can do this classification for us, right? So the first approach I took was the convolutional neural network. So if you're unfamiliar with how a CNN works, what it essentially does is it creates a feature map. So a feature map, in kind of simple terms, is just like a way for the program to kind of classify what the most distinct features of an image are. And then use an activation function to introduce nonlinearity. So this allows the program to establish more complex relationships. Pooling is then introduced. So all the feature maps condensed from all the training data, kind of just gets, merged to create like, yeah, this is the threshold of what a dog audio looks like or a bird audio looks like, essentially. This then creates our fully connected layer, which helps with classification. And then obviously, we have to train the model and, the final output is the classifier itself. So now I want to dive into the architecture, and I'm going to point out a couple things because this project is still like technically a work in progress for the initial scope of the project. So I'm going to point out a couple things that are meant for later development for further, to make this program essentially better. So first things first, we have the required imports. We have the past definitions that I mentioned earlier. And then this essentially allows us to use a GPU to help it run faster. So first things first, we have to generate the audio data set, right? So this function creates our spectrograms to, create the image classification for the program to work with. So for example, you'll notice over here that there's augmentation, data augmentation as well. And I'll go over this a little more in detail later, but the reason we, augmented data is we need to create, a bigger sample size. So the program would have sufficient things to train from. So yeah, this is the data augmentation function, pretty simple. You can stretch how long it takes, the speed control, this is pitch control. This adds random noise to make it so, the audio can essentially be different. And then after that, we have the actual audio classifier. So this essentially modifies there's a fly on my computer. This essentially modifies the shape, so the classifier can work with it, and then the ReLU activation layers, essentially analyze the patterns of each individual shape. So I had these print statements and I commented them out, and this is just for debugging purposes, but if I were to not comment them out, you can see how the shape of each layer gets changed throughout each of these function calls. So next thing is the training function. And this is just a pretty classic, PyTorch training function. Assigns all the training data has the data loader, processes the prepared data, iterates over all of the audio data to have the spectrograms get processed, and then output predictions are generated, and that's pretty much that. Next thing is the audio classification. So we have the temporary labels assigned, which helps us classify whether it's from a dog, bird, and then you notice there's another label, which is other, and this is for something I'll go over later, but it's pretty much I was trying to implement anomaly detection into this, but I'll go over that process when we go over the challenges. So yeah, then we just kind of put it all together. The data gets processed, the training and testing data sets are made, and then everything gets classified. The model gets trained, and then we have a scheduler over here, which slows the learning rate, and this helps increase accuracy because a slow learning rate gives the model more time to process the data. So yeah, then we train and evaluate the model, and you'll notice that I only have one epoch, but ideally you want to do something like 20 so the model can train properly. The reason I did one was just for demonstrative purposes, but ideally you want to do 20. And then yeah, so then we can feed it an audio file. So in this case, this dog single is a file path to singular wave file, same with bird single, and the audio classifier utilizes the labels, the predicted labels that we went over earlier in order to kind of classify the audio. So after that, you can kind of just see the output. Even with one epoch, this program is decently accurate at like 97%. And then you can see that when we feed the audio, when we feed the trained model, the dog audio, it's able to accurately predict that, yes, it's from a dog, and then same thing from a bird. Yeah, sure. Let me get those audios up for you guys. So this is the dog audio. Make sure my audio is on. And then the bird audio. And then, this folder is filled with just sounds like that. So that's pretty much the CNN model. pretty simple, pretty straightforward. And now we going to the vision transformer. So a vision transformer, this model tends to be more accurate over time because of how it works, which I'll go over right now. So what a vision transformer does is it divides an image into patches, and you can specify patch size, but generally, or pretty much all of the case, you want the patch size to be like a multiple of the total image dimensions. So for example, if you have an 8x8 and if you have an 8x8 image and then you have patches of 4x4, then you have 4 patches because total dimension 16, then 4x4, or the total dimension 64, 4x4 patches, 16. Yeah, simple math. And pretty much what it does is it takes these patches and it tries to build a relational understanding of what exactly this image is and how it can classify it into patterns. So an embedding is essentially a numerical representation of these patches. And once the program divides the image up into patches, it can build a relational understanding via these embeddings. So these vectors are then one hot encoded, which is pretty much just using, like, how do I describe it? You can use like ones and zeros to represent different categories. So we'll kind of, it's easier to explain when you kind of see it in the code. And then a self-attention mechanism assigns important scores to the patches. So for example, certain traits are assigned to be more distinctive than others. Residual connections are then made for processing efficiency. So essentially just remembering what the most important traits are. And then the data is normalized for stability. And then obviously we train the model. So what's nice about a vision transformer is that it can be pre-trained, which means that it's trained on not only the data sets you provide it, but data sets that it's worked with over time. So that way it can be more accurate and say, yeah, this is from a dog, this is from a bird, whatever, if anyone else has done like a project like that. So going down to it, going back to similar with the CNN, this function creates our spectrograms. This function processes the files in the folder. So essentially this just creates like a list of all of the files in each directory, and then shoves it in the make spectrogram file to essentially create each audio file into a spectrogram. This assigns labels to each of the spectrograms. So pretty much it sticks the spectrograms with the dog folder with the label 0 and then 1. And then this is the encoding pretty much. And then this is our augment audio, which we discussed earlier. So this is the vision transformer model, and you'll notice that we standardize the image dimensions to fixed dimensions, so we can use a patch size of 16. And we ensure that the model is pre-trained, so we can, use that data from, prior models. And then so something you guys might notice is I use categorical cross entropy instead of binary cross entropy. And this is because what I'm demonstrating to you right now is kind of just like a retrofitted of what I was working on, which I'll show you guys later. But pretty much for a two problem classification, you ideally want to use binary classification because that way, you only have to work with 2 things. But the reason I did categorical cross entropy was eventually I was trying to create a 3rd class, which was other. And you guys saw like an inkling of that in the CNN as well. So yeah, we have our learning rate scheduler, which is the same model as before, just it slows after the 4th epoch, it slows the learning rate by 10%. So learning rate scheduler, and then has our validation data via our test data and test labels, and we do a train test split later on. We have our evaluation over here. So this just pretty much what this does is it makes a prediction via seeing like but because the softmax activation gives us probabilities for what each of the classifications are. This essentially says, okay, when we take the max, like the maximum or let me take whichever one is most likely and then assign a label to it pretty much. This is our schedule that I was talking about earlier. And this was this part of the code was something that it's like a threshold to determine if, say that a prediction isn't entirely solid, then it can return other, but the implementation for anomaly detection hasn't necessarily been finished, so you won't usually see, or you shouldn't really ever see the other prediction pop up.
So you decided on the threshold by experimenting.
Yeah, absolutely. Because, there was a couple bad files that I got rid of in the data set. And those worst files had pretty low confidence scores. And it was just around like 0.79, 0.8-ish. So this is like, these numbers came, the 0.8 just came from experimentation, but since anomaly detection isn't implemented in what's on screen right now, you shouldn't see other generally. So yeah, then we just have this gives us our training and validation loss graph, and over more epochs, you can see that, and this essentially just tells us whether the model is overfitted or not, overfitted, underfitted. With more epochs, the graph should show up, but if we scroll down, we'll see that the graph is empty because I only did one epoch. I would have shown you guys 20, but that takes like 10 hours to load on my laptop, and I didn't.
You should run it on the server.
Yeah, I can probably run on the server.
One question: What was the gap between validation and training losses? How much was the balance? How much was the balance?
We can pull that up right here.
I can't read it. If you could read it.
Yeah, so the validation loss is 0.1688. And then the precision is 0.9349.
And what's your training loss?
My training loss. I don't think I have that on hand right now.
That should give you an idea of the degree of overfitting.
Oh, just like the regular loss, that's 0.2572.
That's odd. Oh no, this is not normalized over number of data points. This is your net loss. Which loss are you using? Cross entropy loss.
Cross entropy, yeah.
Is it normalized? How can your main loss be more than your validation loss? That's a bit odd.
Yeah. Anyway, so
most likely it's your net loss. It's not normalized. It's
yeah, I think it's a net loss. Yeah. But yeah, where was I? Okay. So this is just a model evaluator. So this gives us a confusion matrix to just see how well the program is doing. So, this is just a plotting and gives us the true classes compared to the predicted classes over here. And then so I was initially going to use clustering as a form of outlier detection, which is why I use the KNN-based predictor over here, K-neighbors classifier. And there's other ways to predict this, but this specifically just uses a neighbor's classifier to determine whether it's from a dog, bird, and then in the other case, other, whatever. And the way it does this is, if you guys remember, the embeddings or the numerical representations of the images. So it essentially just plots the embeddings and then uses the neighbors to make a conclusion, pretty much. So this was an attempted form of outlier detection, but it wasn't very effective. So yeah, and then as usual, same as the previous model, process the data. We went over the prepare data function. and then creating train test split, and then using our labels that we defined earlier, with the dogs being 0, birds being 1. And then compile our model, train our model, evaluate our model, print the accuracy. So as you can see, the accuracy is lower compared to the CNN, but this is only because we did it over 1 epoch. Over 20 epochs, the VIT does end up outperforming the CNN by approximately 1%. With the CNN, I believe over 20 epochs, we got around 97-ish%, oscillated kind of between the higher and lower ends of 97, in terms of like 97.01 to like 97.8, stuff like that. This one's able to hit the higher ends of 97 to around to like the lower ends of 98. So over time, this does outperform the CNN, but you just need to give it more training time. So yeah, then we just use the KNN predictor that we, went over earlier. And as you can see, if we feed it the bird single that we were talking about earlier, correctly predicts it's a bird. Feed the dog single that we were talking about, that we showed you earlier, then it correctly predicts it's a dog. So yeah, this is a confusion matrix. And something I want to point out, I guess actually we can go over why the
use the KNN?
it was initially just meant to be a form of outlier detection. I thought that maybe the embeddings for if I just fed it like a random file would be kind of messed up, and then the clustering would essentially just be like, oh, this isn't close enough to either cluster, so it would be classified as other. So that's why I used KNN to begin with, because it was the first attempt at outlier detection. But it didn't end up working, and the reason it didn't end up working was because I'll go over this in more detail later, but the main idea was that when I tried to train the model on, so there's 2 methods I used for outlier detection. The first one, which was I created a database full of audio samples of just random noises. But the problem is that those random noises weren't uniform. Like, for example, that folder with other contains sounds from different animals such as sheep, cows, whatever, but it also has data from like planes taking off, from glass breaking, stuff like that. And if you have so much variety in data, and then you say shove this all into one class, it destroys the accuracy and everything gets messed up. So yeah, this is the confusion matrix. And you'll see like there's a lot of misclassifications on the dog. And this is partly because I ran into a lot of trouble finding a good data set for dog audio. While with birds, there's just a gajillion data sets out there. So finding bird audio was not an issue whatsoever. So that's the general idea behind the CNN.
Data from the Audubon Society? Is there data set available?
From the Audubon Society, I don't think I used that. There's a couple good bird data sets on Kaggle. Yeah, and then for dog audio, I had to combine a couple data sets. So yeah, that's just the general overview of each model. So now I want to compare the two. So first things first, let's go over the pros and cons for the CNN. So first things first, the CNN has good feature learning. So obviously you can extract relevant features from data, which helps with image classification. And that's essentially the foundation of both models. It converts the audio into an image, and it's essentially an image classifier. It has good hierarchical representation, so you can have more complex structure recognition. Translation and variance, it can recognize patterns regardless of location within the data, so it can, compare data pretty far apart. And then obviously it's less intensive. Some cons that it's data hungry, but in general, it's good practice to already have a big data set. So this isn't that big of a deal. It can be intensive if you run it on your CPU. Getting information out of a CNN can be difficult. And it's not really flexible. So you can't use it for it's more difficult to work with if you're not trying to do just image classification, while with vision transformers, it has a little more potential. So with a vision transformer, long range dependencies, so it can recognize patterns that are far apart. It's very scalable, so you can use it for any data set size and any model size. It has unified architecture. So for example, CNNs are primarily used for image classifiers, but vision transformers can be even used for things like text. And then the vision transformer is extremely easily trainable. And part of this is because you can also get a vision transformer that's pre-trained. This may be a hardware limitation, and I'll go over this in some of the challenges I faced, but the VIT is obviously very computationally intensive. It took a lot longer for me to run the VIT on my laptop compared to the CNN. It's very data intensive. For example, I wasn't really able to hit above 70-80% accuracy with a sample size of maybe 200-300 sounds, while the CNN was able to do so. But once we started hitting the thousands, we got back to our 90s and in terms of accuracy. So this meant that I had to supplement it using augmentation, which is fine. It's not too big of a deal, but it's just mainly it's more computationally demanding. So which is better? I think it depends on your use case. If you have larger data sets and you have the computational efficiency, I think you should go with a vision transformer because it's generally more accurate and it's more powerful. But if you're limited in your data sample size, for example, if you're collecting the data yourself, a CNN might be a little better. So a couple of challenges that we ran into during this whole process was firstly computational limitations. So my laptop is a MacBook Pro M2. And because of this, I ran into a whole ton of just random things not working out because this is a fairly new laptop. So not everything has been updated to, work with the chip I'm using. So an example of this, as I was discussing earlier, was the vision transformer CNN, intensive, one being more intensive than the other. I couldn't get CUDA working with my vision transformer because installing it on an M2 was extremely unintuitive. Another example is we use the Atom optimizer, and the Atom optimizer is pretty good. It's flexible. I wanted to use Atom W, but Atom W wasn't working with my chip, so I couldn't. And then if I want to use something like a TensorFlow CNN, for example, that also did not work with my chip. So I had to do a whole ton of awkward workarounds because of my hardware limitations. So that was the first challenge we ran into. Second yeah. The dataset size was another challenge. So as I mentioned earlier, getting the bird sounds was not really an issue. But I will literally give you like $10 million if you can find any dog data set size, any dog data set on the internet that's open source, that's like above 100 files. Like if you can find me that, like I will literally give you my firstborn child.
I remember that.
Yeah. I am unfortunately petless, but yeah, I don't know. Maybe I could steal one of my friend's dogs or something. In any case, finding the data set was honestly probably the biggest struggle because right when I thought I hit gold with my dog data set, I ended up listening to it. I was like, wait, why is my accuracy so low? And then I listened to all the sounds and I'm like, these are not dogs. So I had to start from scratch pretty much on the data set size. So although it's elementary, I will say that having good data for your data set essentially makes or breaks your model. And even finding something as simple as a data set can literally take you days. So just, something to have a heads up for. Finally, outlier detection. So this was the big thing that I was hopefully going to be able to show you guys, but unfortunately I wasn't able to get it done on time for this presentation. So pretty much outlier detection. I mentioned the KNN from earlier, K-neighbors classification. That was the first attempt at outlier detection. So the main problem that we're running into. So the first attempt of the outlier detection I used, I think it's probably in this one. I think it's version 6. Yeah. So the first attempt I used for outlier detection, which didn't really work, was I created a huge folder full of random sounds. And so these random sounds are just like ambient noise, cat noises, like whatever, just random stuff. And I wanted to essentially create a third class, which is why we use categorical cross entropy, because I wanted to create three classifications instead of 2. But the reason this doesn't work is because the variability within the data. So if you actually end up running this program, I did a keyboard interrupt, but you can already see through the first couple seconds of the epic training, these stats are pretty bad. Like you have 80% loss, pretty horrible precision. And although it's very short into the epic training life cycle, these stats don't get better. Trust me when I say they don't get better. I was hitting 75-80% accuracy, which is not something you want for a vision transformer. So I had to toss this idea of the window of just using a data set full of random noises and then feeding it another random noise and saying, hey, maybe it'll fall under this umbrella of random noises. That wouldn't work. Now, if I wanted to really be, ultra dedicated, then I can create like a class for sheep, class for ambient noise, class for rain, class for glass breaking, but that's not practical because that's too many things I have to account for. So the next attempt that I was trying to use, that I wasn't fully able to get working in time for this, was a recommendation from my good friend Dennis, which was using an ISO map. But I just couldn't get it working, and there's just in time for this presentation. So I think it has potential because during the first couple run throughs, it was able to classify birds accurately. But if I fed it, I think I might have accidentally deleted the code here because I was trying to change it around. But you can kind of just see the remnants from when I did try to run it. It was able to classify birds properly, but if I fed it dog audio, it was unable to differentiate between dogs and other. So I probably just need a larger data set for that. And I might need to tweak around with some hyperparameters. But this approach could have potential, but I wasn't able to get it working in time.
Sure. Did you try any of the deep anomaly detection techniques?
Not yet. No. Yeah. But yeah, that pretty much concludes what I've been working on. It's a pretty fun project. This is the first time I've done anything remotely in this field, so just tried my best to learn everything, and hopefully I'll be able to answer any questions to the best of my ability. But yeah, that's my presentation. Hope you guys enjoyed. Sorry for taking so much of your time, but appreciate it.
Excellent. Well presented.
Thank you.
Well presented.
Yeah, on them too.
Yeah, that's the one thing I want to tell you. No, it's a Mac laptop, so you need to use metal laptop. Which are not CUDA. So we don't have CUDA on
So CUDA is only for NVIDIA, right?
Yeah.
I was confused. Why were you trying to? So you have to have.
Yeah, I mean, it's just like if I run it on the CPU, it takes.
No, you
Yeah.
should use a metal. Yeah.
Okay.
Framework for Apple.
Okay.
In my basic recommendation stance, if you want to do AI,
Mhm.
you start by donating your Macs to someone else.
Yeah.
We can use even Google Colab.
Mhm.
So you get A100.
Okay, yeah, I'll probably
Yeah.
get on that so I don't have to wait 7 hours between each
Yeah.
test run. Yeah.
Actually, this is a new thing. It's
Mm.
for $50 a month.
Mhm.
Now they give you access to A100s,
Mhm.
and that will make a pretty quick job out of your training.
Yeah.
500 compute units. So I don't know what compute unit, but
But it's more than. That's what I see.
$50 is 500.
Yeah, only 500 complete units is more than.
So what is one compute unit?
I don't know that exactly, but people.
It's their own definition. No one really
Yeah.
knows.
So if you say 500 hours, then how is good? It's very good.
Anyway, so if you just leave it. So I'll get back onto the report.
Thank you, thank you.
So
So guys, first of all, thanks a lot for being here for the presentation. And Shrutik, this is amazing job, amazing internship. Going forward, finish the DAD. Apply the DADs to it and see where it takes you. It's an important step to do. You identified the good technical points. See, when you take random song, there's a difference between random as in truly random, like as in Gaussian noise versus a random uniform noise or white noise, versus randomly picking up sounds or sound files is not random because they belong to something. It belongs to a truck. It has a pattern. It belongs to a cat. And so this will confuse the model for sure. And that's probably one reason why you couldn't get out of it. Anomaly detection from that perspective isn't good. One approach that you could do potentially is use an autoencoder. Well, you haven't taken that. When you take the deep learning course, you'll realize that one possibility is that you project it into a latent space in such a way that you force all the dogs to go into one region of the latent space and you force all the birds to go into another region of the feature space. So whenever you take a point, you look at the net reconstruction loss. If you get a sound that is neither a cat, neither a dog or a bird, the reconstruction loss will be high, and you know that this is a wrong file. Yeah. So those things will come to you when you take the neural. It's for you who has practically no background in this field at this moment. This is already very impressive work, but then follow it up with more systematic learning, and you will see a difference in that thing. But once again, this is an amazing job. I hope you continue to be associated here with us. It's a pleasure to have you here, and a very, very successful internship. Guys, very successful. Thank you. Thanks for having me. All right, guys. So with that, we move on to the third item. Any comments, guys? Any questions for Shrutik before we move on to the next item? Any comments? Go ahead.
Firstly, you did extremely great job. Secondly, your task was distinguishing bird audio files from audio files, right?
Yeah.
So, what went into choosing like vision models?
Like why a vision transform?
Yeah. Or even like a content person for like images.
Yeah, a vision transformer is just more powerful, more accurate, more scalable. So I don't know, it's just recommendation by one boss. So, yeah.
It sort of works. Yeah. Most of these guys who are doing, like if you look at PyTorch audio, etc., the standard models, somewhere along the lines, people have tried many, many approaches.
Yeah.
They have looked at the Fourier transform, they have looked at audio snippets as a data file itself, and many approaches have been tried. Recently, like for this kind of a problem, which is in a way straightforward, and the difference is quite high between a dog and a bird. When you look at the spectrogram of the two, you can literally visually tell them apart, because visually they are distinguishable, right?
I see.
Therefore, a vision transformer makes sense.
Yeah, that makes sense.
Audio is somewhere that is a Fourier transformation.
Yeah, it's a sound wave. So you can do a Fourier transform, and you can look at the spectrum of it. And that's not very far from the spectrogram. It's somewhat along the same lines, yeah.
And internship for what?
Sorry.
It was a summer internship.
Oh, summer internship.
Yeah.
I thought
So
it
we
was
had 6 fairly successful summer internship. This was actually one of the very good ones.
It's a better project than mine. I finished in masters. But very complicated.
Nice. Great job again. So guys, please stay back for lunch. I'll go and get lunch now. So you guys can continue talking and I'll take a break. It takes about 10 minutes to go, 10 minutes to come back. So in 20 minutes, lunch should be here. I'll go get it. Anybody who wants to accompany me is welcome to join me.
Is the presentation, all that done? Time to finish